Ever wonder what makes your smart devices, well, smart? It's definitely not magic. See, from your coffee maker to your car, there's this hidden world of intelligence at work. And right now, we're going to pull back the curtain on the tiny, tiny brains that power pretty much everything you own. Okay, so let's start with a quick question. Just think about it for a second. Your microwave, your car, your TV remote. I mean, they seem totally different, right? One heats your food, one gets you from A to B, and one just changes the channel. But underneath it all, they share this fundamental secret ingredient. And there it is. That secret ingredient is the microcontroller. You can think of it as a miniature, totally dedicated computer that gives these devices their job, their purpose, turning what would be a simple machine into a really useful tool. So what is this tiny brain really? Let's break down what makes a microcontroller so special and honestly so incredibly useful in our everyday lives. Here's the thing. A microcontroller isn't just a processor. Nope. It's an entire computer system that's been squeezed onto one single tiny chip. It's got everything it needs to get the job done. A CPU, the central processing unit, to do all the thinking, memory to remember its instructions, and all the little extras, the peripherals, to interact with the outside world. It's the whole package, an all-in-one solution. So you might be thinking, how is that different from, my laptop? Well, think of your PC as this powerful, do-it-all beast, but it's also hungry for power, and it costs a lot. A microcontroller is the exact opposite. It's a specialist. It's designed to do one specific task and do it really well. And because it's so focused, it's incredibly small, it sips power, and it's so cheap, we're talking just a few bucks, that we can put them inside billions and billions of devices. All right, let's crack this thing open and see what's inside. At its very heart, a microcontroller has two main parts that work together to bring it to life. The part that thinks and the part that remembers. The best way to picture this is to think of a chef in a kitchen. The CPU? That's the chef. It's the one that follows the instructions and does all the work. But even the best chef needs a recipe book for the instructions and a pantry for the ingredients. That's the memory. It holds both the program, which is the recipe, and the data that the program needs to work with. Yep, the ingredients. So how does the the CPU, actually do its job? Well, it runs on this constant, incredibly fast cycle. First, it fetches an instruction from memory. Then it decodes that instruction to figure out what it's supposed to do. And finally, it executes the action. Fetch, decode, execute. This simple loop just repeats itself millions of times every single second, and it's the basis of everything the chip does. Okay, so it can think, but a brain in a box isn't very useful, is it? It needs to be able to interact with the world around it, and this is where the microcontroller senses come into play. This connection to the real world happens through something called GPIO pins. That stands for General Purpose Input-Output. You should really just think of these little metal pins as the microcontroller's senses and its voice. They're the physical connection points that let its digital brain talk to our physical world. They are its eyes, its ears, and its hands. So through these pins, when they're set up as inputs, the microcontroller can sense stuff. A classic example is just a simple button. When you press that button, the voltage on the pin changes. The microcontroller sees that change as a digital signal, a 1 or a 0, and boom, it knows something just happened. And then what happens? It acts. It can use other pins, configured as outputs, to do something in the real world. So it can send a high voltage signal to a different pin, giving it the power to turn on a little light, an LED. This simple 1-2 punch, sensing a button and lighting an LED, is really the foundation of almost every electronic gadget you've ever used. But wait a second. For any of this to work, everything has to happen in perfect time. It can't be chaos. The microcontroller needs a steady, reliable rhythm to keep everything synchronized. And that rhythm comes from something called the clock signal. It's just a constant ticking electronic pulse. It's like a metronome for the chip, or maybe even better, a heartbeat. Every single thing it does, every fetch, every decode, every execute, is timed perfectly to this pulse. It's what makes the entire system work in lockstep. And the speed? It's just mind-blowing. A typical microcontroller, like the one we're looking at here, can have a clock that beats 168 million times every single second. That's how many chances it gets to do something in the blink of an eye. It's incredible.
Now, the chip has these special little helpers inside called timers, and their whole job is just to count these super fast clock pulses. By counting this incredibly steady heartbeat, they can measure time with amazing precision and make sure things happen at exactly the right moment.
This precise timing lets us do some really clever tricks. One of them is called pulse width modulation, or PWM. So imagine you don't just want an LED on or off, you want to dim it. With PWM, you can flash that LED on and off thousands of times a second, way too fast for your eye to notice. By changing how long it's on versus off in each of those tiny flashes, you can actually control how bright it looks. And this exact same idea is used to control the speed of a motor or even to make a speaker play a specific note. Pretty cool, right? Okay, so we've got a chip that can think and sense and act. But, in the real world, it's a team sport. One chip rarely works all by itself. They need to be able to talk to each other. Your microcontroller might need to get location data from a GPS sensor or send an image to a screen or maybe coordinate with a whole other microcontroller. To do all this, they use what are called serial communication protocols. Just think of them as different languages designed for different kinds of conversations. So let's break down the big three. First up is UART. This is like a simple, direct phone call between just two devices. Nice and easy. Then you've got I2C. This one is more like a conference call. It lets one master chip talk to a bunch of slave devices, like different sensors, all using the same two wires. And finally, there's SPI. Think of this as a super fast business meeting. It's much quicker and lets chips have complex two-way conversations at the same time. The main takeaway here is that engineers just pick the right language for the right job.
So let's just do a quick recap of the fundamental building blocks we've covered. We've got the core brain, right? The CPU and memory. We've got its senses and voice, the GPIO. We've got its heartbeat, that's the clock and timers. And finally, we have the languages it uses to talk to all the other chips.
These four things, they are the foundation behind almost every single embedded system out there. Now, you might sometimes hear people use the word microprocessor. And while it's related, what we've been describing this whole time, this all-in-one chip with the brain, the memory, and the senses, that is a microcontroller. And whether it's inside a simple kid's toy or a life-saving medical device, these are the concepts that make it all work. They are the invisible engines of our daily lives, just quietly powering our world. So the real question to think about is, as they keep getting smaller, cheaper, and way more powerful, what incredible new things are they going to build for our future?